Let's move on to talking about absolute dating techniques that are good for archaeological sites where fossilized human bones are not found. But let's start with a quick review of dating techniques. What are the two major categories of dating techniques? Relative dating and absolute dating. Which one tells you a year or a range of years? Absolute dating. Which one tells you only that something is older than or younger than something else? Relative dating. The relative dating techniques that I talked about included stratigraphy, seriation, two types of seriation, stylistic seriation or frequency seriation, bone chemistry analysis, and I gave the example of fluorine analysis, geochronology, and the index fossil or faunal succession concept. The absolute dating techniques I talked about that are good for paleontological sites with fossil human remains included three radiometric techniques: potassium-argon, argon-argon, and uranium-lead. But I also talked about geomagnetic polarity, fission track dating, and electron spin resonance. Today, the topic is absolute dating techniques used by archaeologists at sites that don't include fossil human remains, that is, more recent sites. I'll talk about the radiometric technique called radiocarbon dating or C14 dating. I'll also talk about dendrochronology or tree ring dating, archaeomagnetism, and two more types of luminescence dating, thermoluminescence and optically stimulated luminescence. We've already spoken about electron spin resonance. As you already know, radiometric dating techniques refer to using radioactive isotopes to date something. Today I'll talk about radiocarbon dating or C14 dating. Here on Earth, during life, an organism takes in carbon isotopes. We are a carbon-based planet. However, after death, no carbon is taken in. Three heavy carbon isotopes exist: carbon-12, carbon-13, and carbon-14. The carbon isotopes are formed by plants during photosynthesis. Animals get these carbon isotopes from eating plants or from eating other animals who have eaten plants. The isotopes of C12 and C13 are stable. That is, after the death of the organism, the ratios that you have of these two isotopes remain the same for thousands of years. And interestingly, they can be used to reconstruct the diet of the organism. And that's because different plants produce different ratios of C12 and C13. So by looking at their ratios in, say, a cow bone, we can tell perhaps what sorts of plants the cow was eating. C14, however, is unstable. It decays to nitrogen-14. It has a half-life of 5,730 years. That is, after death, when no more C14 is accumulated, after 5,730 years, half of that C14 will have decayed to nitrogen-14. There are a number of constraints to using radiocarbon dating. First of all, you can date only something that is organic, that is, that used to be alive. And you need 5 to 10 grams of it. This wouldn't be a big deal, except that you destroy what you date. So if you want to date something, you have to destroy a pretty big piece of it. And it's not cheap. On top of all of that, it's not very accurate. What you get back is only a range in years. And at the 1 sigma, you get only a 2 in 3 chance of being correct. It's dependable for only from about 200 years ago up to 50,000 years ago. The date that you get back is in radiocarbon years before present. which are not the same as our calendrical system years, so it must be calibrated to read in our calendrical system. This technique was invented by Willard Libby, who won the Nobel Prize for inventing radiocarbon dating at the end of World War II. So he published on this in 1949. He won the Nobel Prize in 1960. Libby set present, or before present, to AD 1950. To my mind, a very short-sighted decision. So example, when you submit your sample to the radiocarbon laboratory, you might get back a date that says 3,000 radiocarbon years before present, plus or minus 50. What does that mean? Well, given that before present equals AD 1950, I have to subtract that number from 1950. So what they meant was 1050 BC. And what's that plus or minus? Well, that's the level of accuracy for this particular sample, and 50 is pretty good. But a different sample will have a different plus or minus. At 1 sigma, which is the date given here, the date has a 2 in 3 chance of actually falling within the range. That is, that this dated between 1100 and 1000 BC. Now, if we double the plus or minus, the date has a 99% chance of being correct. That is, 1150 to 950 BC. Here's an example of the report that you get back from the radiocarbon laboratory. You can see that they give you both the 1 sigma probability, the 68.2%, and the 2 sigma probability, 95.4%. But you can also see that you never get back an exact date. What you get back is a range of dates. So radiocarbon dating is not that accurate, and it's expensive. However, the accelerator mass spectrometer method was developed. This is more expensive, but it needs only a few milligrams rather than the 10 grams needed for regular radiocarbon dating. As a result, you can date something as small as an eyelash instead of destroying 10 grams of your sample. This led to scientists dating the Shroud of Turin because they could take just a thread rather than take a chunk out of this very valuable artifact. So AMS dating is radiocarbon dating. It's just using a different set of lab equipment. 3 different labs did AMS dating on the Shroud of Turin. And what they found was that the shroud material dated to 1260 to 1390 AD, which is more than a millennium after the life and death of the historical Jesus. However, this shroud still remains unexplained. Let's talk now about dendrochronology, or tree ring dating. Dendro, referring to trees, chronology, time, tree ring dating. It is used to date wood from archaeological sites. It is the most accurate absolute dating technique. Unlike radiocarbon dating, it gives you an exact year, and not only that, the season when a tree was cut down. This technique was developed by A.E. Douglas, who was an astronomer interested in sunspots and tracking climate in the past. It looks at the relative width of annual tree rings. Dendrochronology is based on the idea that the amount of tree growth, and therefore the width of each ring, differs each year according to climatic factors. So as you can see, you might have a year where the tree doesn't grow very much, and a year where the tree grew very well. However, as you know, climatic patterns, and thus the growth patterns, should be localized to different regions. So the weather in South Carolina is not the same as the weather in Arizona, or the weather up in the northwest coast. So to use dendrochronology, you must build a master key for your region. Now, archaeologically, you're not setting out to date trees, you are dating wood. You can date dried wood, such as can be found in architectural elements in dry areas like the American Southwest. Or you can date charred wood, such as this shipwreck timber. As I mentioned already, to use this, you must have a regional master key that you've built up. How do you do this? Well, you start with coring a living tree. So it doesn't need to be a tree stump as is illustrated here. You can actually stick a stainless steel core into the tree and take out a pencil-sized piece of wood. You then look for, say, a dead tree, and then you would look for, say, a house timber from a historic house. And so you keep trying to find something older and older with rings that overlap, skinny, narrow, with the rings from your first tree. So you build back in time, extending the tree ring sequence back to build your regional master key. There's some constraints to using dendrochronology. First of all, not every tree has different size rings from year to year. If the tree is growing in a very nice floodplain, perhaps it's always got water coming to its roots, and it's often water that is the determining factor, or basically climate. So you need wood from a sensitive tree, that is a tree whose rings differ from year to year. You also need wood that still has an outer ring with the bark on it, because what you're dating is the year that the tree was cut. So you need to see, aha, here's the bark, here's the outer ring. The tree, this is the year that the tree was cut down to get the wood. And you need a regional master key. Now, how far back you can date depends on the development of your regional master key. The southwestern United States has an unbroken sequence that goes back over 2,000 years. Here in South Carolina, we now have a regional sequence of bald cypress that goes back 500 years. In Germany, they have a sequence that goes back 10,000 years. So how far back you can date depends upon your regional master key that you've built up. So remember, dendrochronology is the most accurate absolute dating technique because you can date not only to the exact year, you can even date to the season that the tree was cut down. As you can see, the cells in the spring look very different from the cells in the fall. And because wood is organic, you can actually scoop out a particular ring and use it to calibrate the carbon-14 dates. I'll talk about a third absolute dating technique called archaeomagnetism. Now, throughout time, the magnetic North Pole has wandered. Now, when I say this is not the same as talking about magnetic polarity dating, when the North Pole and the South Pole switch. In between, when they switch, the poles are wandering around. This illustration shows you a 120-year period from 1900 to 2020 of where the magnetic North Pole is compared to the geographic North Pole. So archaeomagnetism is based on the idea that as something was magnetized in the past, the particles in that object pointed to where the magnetic North Pole was at the time. So let's say you have an archaeological site here where the red X is. And at AD 800, anything that was magnetized would have pointed this direction. Versus at AD 1150, they would have pointed way over to here. Now you can see right away that this is more complicated than I'm making it sound because this line pointing to AD 1150 crosses two other time periods. So many materials contain magnetic particles that become aligned. And you can get both natural magnetization and cultural magnetization. Usually, archaeologists are interested in cultural magnetization. So, for example, you can get things from thermal magnetization when something is heated over 700 degrees centigrade, or from chemical magnetization, or from depositional magnetization, such as a river floods, and as the silt settles out, the little silt grains will align themselves facing magnetic north. Thermal magnetization is especially useful for archaeologists. For example, during heating, a clay hearth, such as you see here, and in fact here in this picture you see two successive clay hearths. These are called puddled clay hearths. That's where they built their fires inside these. And because these were heated over 700 degrees centigrade when they were used, the clay particles in them will tell us what direction magnetic north was at the time that the hearth was in use. To submit a sample for archaeomagnetic dating, you have to cut these little columns and take the sample, but you have to record the present-day location and the exact present-day orientation so that they can compare that against the prehistoric one. So you can date magnetized objects up to about 10,000 years ago. The sample that you take is enclosed in plaster and sent to the laboratory, where it's put into a machine that finds out where the magnetic field faced back when the object was used. So for archaeomagnetic dating, you need to work out your regional variation. This has been a very popular dating technique in the southwestern United States, where it is accurate within 20 to 40 years. Much better than you get with C14 dating, and certainly much cheaper. I'll end by talking about luminescence dating. And there are three types of dating, two of which I'll talk about today. So after burial or heating, minerals absorb natural ionizing radiation from the surrounding sediments or from the sunlight. And dating is based upon measuring the amount of light that is released on either reheating or reshining a light on minerals such as quartz and feldspar. So, upon either giving it thermal or optical stimulation. And the light that you get at that point indicates the radiation dose that had accumulated in these minerals through time. So when exposed to sunlight, as in the case of sand that got buried, or in the case of pottery, when it's heated hot enough again, the clock is set to 0. So if you were dating sand grains, quartz sand grains, that got buried, you would date the last time that they were on the surface of the ground with the sun shining on them. Or if you're dating pottery, you're dating the point at which that pottery was made and fired. So one of the types of luminescence dating is called thermoluminescence. And as you might guess from the name, it talks about heating. So it dates the accumulated dose of radiation since the material was heated to over 400 degrees centigrade. So you could date pottery or tiles, bricks, or heat-treated chert, or even lava. And as the material is reheated during analysis, you measure the weak light signal. It can date something from a few hundred years old to at least several 100,000 years old. Optically Stimulated Luminescence, or OSL, measures the last time the sediment, or actually, say, the quartz grains in the sediment, was exposed to sunlight. To measure this, you re-expose the material to an intense light to measure the signature. It can date something from a few hundred years old to over 10,000 years old. When you're collecting this kind of sample, you have to keep it in the dark until you're ready to measure the signature. So people pound in PVC pipes that are black and take those back to the laboratory because you don't dare let any sunlight hit the stuff until you're ready to measure the signal. So the three luminescence techniques are based on the measurement of trapped electronic charges that accumulate in crystalline materials as a result of low-level radioactivity. We'd already spoken about electron spin resonance, and today I talked about optically stimulated luminescence. Usually an archaeologist just calls it OSL, or thermoluminescence, and again the archaeologist may simply refer to it as TL. To act as a clock, the electronic charges must be zeroed by heating, as in thermoluminescence, exposure to daylight, as in optically stimulated luminescence, or growth, such as the electron spin resonance on fossilized teeth. So what's the takeaway information? I want you to recognize which are absolute and which are relative dating techniques. And especially important in relative dating are stratigraphic analysis, which is based on the law of superposition, and the index fossil or faunal succession concept. Especially important in absolute dating are the radiocarbon dating technique and potassium-argon dating technique. For the important absolute dating techniques, know what materials can be dated. For example, for potassium-argon, you need volcanic tuff. Or for radiocarbon dating, you must date something that is organic, and how far back in time the method can date something. Later, when we talk about the fossil record, you'll want to know which dating technique is used for which areas where fossils occur in Africa. So recognize which absolute dating techniques are radiometric and understand how radiometric dating works, knowing the half-life of something and measuring the ratio left of that something. So which dating techniques are used where and when? Well, stratigraphic analysis is used at every archaeological site and every fossil locality every day that you're at the site. Archaeologists and paleoanthropologists are always thinking about their stratigraphy. The index fossil concept is useful for dating early human fossil localities in South Africa, where there has been no volcanic activity, but where we do have animal fossils along with the early human fossils. The premier dating technique for early human fossil localities in East Africa, where we do have volcanoes, is potassium-argon dating or argon-argon dating. Now, radiocarbon or AMS dating cannot be used to date early human fossil localities because it can date back only to 50,000 years ago at the very most. However, when we start talking about modern humans, we will rely on C14 dating of sites. So radiocarbon or AMS dating can't date far enough back to help us with early human fossil localities, but they're frequently used to date archaeological sites that are less than 50,000 years old. Whereas potassium-argon and argon-argon are major dating techniques to date fossil localities in areas like East Africa, where there has been volcanic activity. Dendrochronology is the most accurate absolute dating technique. It can tell us not only the exact year, but even the season. But it can only be used in areas where you have a master key. And so far, the oldest master key goes back only 10,000 years. Dendrochronology is used to calibrate C14 dates. Now remember, dendrochronology, you're looking at tree rings. What archaeologists recover is wood. And of course, there's more to it than I've talked about here. For example, perhaps when you're building your house, you reuse lumber from an older house. Or maybe you stockpile your lumber until you've accumulated enough. So the archaeologist has a lot of interpretation to do. It's not just as simple as always dating the wood and thinking that it's fresh cut. Archaeomagnetism looks at magnetized particles, for example, a fired clay hearth, and it can date back as far as 10,000 years ago. The three luminescence techniques are based on the measurement of trapped electronic charges that accumulate in crystalline materials as a result of low-level radioactivity. So to act as a clock, back then, when these objects were used or exposed to sunlight, electronic charges must have been zeroed by heating, as in thermoluminescence, exposure to daylight, as in the sand quartz grains in optically stimulated luminescence, or growth, such as how electron spin resonance can measure fossilized teeth or speleothems or shells. So what levels of knowledge do I expect to test you on? Well, I expect that when I give you a list of dating techniques, you can separate out which are relative and which are absolute dating techniques. And I expect you to be able to distinguish which absolute dating techniques can be used to date early human fossil sites that are millions of years old. And you can distinguish which absolute dating techniques can only be used for archaeological sites that are not that old, that don't contain fossilized human bones. For relative dating techniques, I especially want you to understand stratigraphic dating, which is used on a daily basis, in the index fossil or faunal succession concept. And for absolute dating techniques, I want you to understand especially potassium-argon and C14 or radiocarbon dating. What materials can potassium-argon be used on? What materials can radiocarbon dating be used on? And what are the limitations or cons to each?